So this is our negative emissions technology presentation. It's by Christopher Cruz, Rece, Gobel, and Liam McCarthy. So just some background on climate change and global warming. The company Microsoft created a goal to become carbon negative by 2030, and by 2050 they wanted to remove all the carbon that they've emitted since its foundation in 1975. So this is a profound statement made by the company, and it underscores the potential for using negative emissions technology and will hopefully set the tone for many other companies, as well as help with the goals to cut carbon emissions. Now, being carbon neutral versus carbon negative, what does that mean? It's pretty simple. Carbon neutral basically means that any CO2 that's released into the atmosphere from human activity is balanced by an equivalent amount of CO2 removed from the atmosphere. And on the other hand, you have carbon negative, which requires a company or sector or country to remove more CO2 from the atmosphere than it's emitting. Now, in order to meet the 1.5 degrees Celsius goal, which I'll talk about in a second, carbon removal is going to be necessary. However, this is not only a long-term solution, but it can also be used in the short term as well to help in the transition just to clean energy. Negative emissions technology can also offset the emissions put off by technically challenging industrial areas, such as steel making, concrete making, as well as long-distance transportation. And lastly, carbon removal can be done via 3 areas: nature-based solutions, enhanced natural processes, and technological solutions. So Chris is going to get into the specifics of these areas in a second, but all of them come with their pros and cons that make them viable options for the future. And while carbon removal is a good compromise to the climate change problems we're facing right now, reducing emissions and switching over to clean technology so that we can eventually produce no CO2 is the main goal, basically, and that's really the only way to stop climate change for good. So again, just some background on the Paris Agreement, which is that 1.5 degrees I mentioned. In 2016, the Paris Agreement is entered into force. So parties at the UNFCCC reached a landmark agreement to combat climate change and to intensify investments needed for a low-carbon future. So this brought together virtually all nations to settle on an ambitious goal for the future. So the agreement made the goal to keep global warming temperatures to well under a 2 degrees Celsius increase and possibly even further to a 1.5 degrees Celsius increase. So basically what this means is by the end of the century, for global temperatures to rise less than 1.5 to 2 degrees Celsius. Now, some of the crucial areas covered by the document include a long-term temperature goal, climate neutrality, mitigation, and the financing of technology and capacity building support. So simply removing carbon dioxide from the air isn't really going to be good enough. We need to lower our emissions for things to stop completely. And this means developed countries such as the US are going to be or should support the efforts of developing countries to build cleaner futures so that they can both develop as well as provide a green future for the rest of their citizens. However, I'll talk about this later in the presentation. The US has actually since backed out of the agreement. So some of the largest contributors to climate change, while CO2, it does actually occur naturally in the atmosphere regardless of human activity, we are rapidly speeding up the amount that's present in it. So the first contributor is consuming electricity, which is about 33% of CO2 emissions in just the US. These numbers all contribute to emissions in the US alone, not globally. Now, however, CO2, it accounts for 77% of man-made greenhouse gas emissions, and there are several activities that are contributing heavily to that. And we're at the point in which we're producing more CO2 than our flora can absorb, which is basically responsible for all that extra and excess CO2 going into the atmosphere. Now, burning coal, which is what's used for about 85% of electricity across the world, that releases twice as much CO2 than another fossil fuel such as petroleum. And as for the second contributor, you have transportation, which is about 29% of CO2 emissions. So this is one of the largest contributors, as about 95% of people in the US have a personal car or have access to a personal car. So it's extremely popular. Obviously, it makes sense that it'd be such a high number. And also on top of this, which I actually just found interesting, was a study of cruise ships, and which is a very popular way of vacation. Going on a cruise ship and going out to sea on vacation emits 12 times more CO2 than doing so on land. And now as for our third one, building, which is 2% of CO2 emissions. And while this is a smaller percent, it is a consistent amount because of just the popularity of the cement and the steel industry in the US. They're used a lot in our infrastructure, and they both require very large amounts of energy to convert raw materials into manufactured products. And lastly is deforestation. So again, this isn't necessarily putting off CO2, but rather it's taking away forests that absorb CO2, which is obviously a huge issue because we already don't have enough flora to absorb all the CO2 that we're putting off. So it's allowing more gas to be emitted into the air.
The coastal blue carbon. Coastal carbon sequestration refers to carbon dioxide removal from the atmosphere in conjunction with the plant growth and the accumulation and burial of plant organic carbon residue in the soil of tidal wetland and seagrass ecosystems. Tidal wetlands, including salt marshes and mangroves, thrive in soft sediment, shallow regions of estuaries between high and mean sea level, while seagrasses inhabit adjacent soft sediment estuarine bottoms with adequate light penetration. Macroalgae systems such as kelp forest, while being extremely productive, do not have root systems and soils to accumulate carbon. Little is known about the fate of macroalgae organic carbon, a portion of which could potentially be sequestered by other means when exported from the macroalgae bed. Tidal wetlands and seagrasses are among the most productive regions on Earth, sequestering carbon dioxide at a rate of 7.98 hectare carbon dioxide for tidal wetlands and 1.58 hectare carbon dioxide for seagrass meadows. They are an important component of the global carbon cycle, in which tidal wetlands grew to their current area extent only in the past 4,000 to 6,000 years, once the rate of sea level rise declined to less than 2 millimeters per year. Terrestrial carbon removal and sequestration. Terrestrial carbon sequestration occurs when the uptake of carbon by plants exceeds carbon losses through soil respiration, plant respiration, and biomass. It is defined as an increase in the amount of maintenance over time of organic carbon and biological stocks, driven by the plant assimilation of carbon dioxide from the atmosphere. Biological carbon stocks are largely controlled by actively cycling processes, that is, assimilation, carbon uptake from the atmosphere, and respiration, carbon loss to the atmosphere. The carbon stocks of interest are those that can accumulate and persist over multi-decadal timescales, namely woody biomass and coarse woody debris and soil organic matter. The assessment of terrestrial carbon sequestration options centers around the predominant types of managed ecosystems, such as forest land, cropland, and grassland, each with multiple management levers to modify carbon stocks. Other intensively managed lands, such as urban/peri-urban landscapes, contain biotic carbon stocks in trees and green spaces, such as parks, lawns, for which of the sequestration practices described under the forest land and grassland category could apply. Wetlands are of particular importance because they contain the highest carbon stocks per unit area of any ecosystem, where they have been drained and converted to crop grazing or forest production approaches to recover carbon sequestration capacity will be discussed under each of the three main land use types. Bioenergy with carbon capture and sequestration. Combining bioenergy production with carbon capture and sequestration can lead to net negative emissions as carbon stored by photosynthesizing biomass growth is sequestered rather than released to the atmosphere. Various technological pathways for bioenergy with carbon capture and sequestration are in 4 steps. One being biomass production. Biomass feedstock may come from forest management, such as tree stems, branches, bark, logging residues, sawmill waste, agriculture, algae cultivation, or a collection of municipal organic solid waste. Biomass sequesters atmospheric carbon dioxide while growing, leading to an initial negative emission. The production and collection of biomass feedstock involves several activities such as seeding, fertilizer and pesticide production, spreading, tiling, logging roads, and tree harvesting. Energy used in these activities is part of the life cycle assessment. 2. Biomass transportation. Biomass must be transported from the source to the conversion facility or end user, where it will be converted to heat, electricity, or other fuels. This fuel must then be dispersed to end users. Biomass conversion. Biomass conversion has 2 steps to it. Thermochemical. Several thermochemical and biological routes for the conversion of biomass to energy have been demonstrated and implemented. Thermochemical routes broadly include pyrolysis, hydrothermal liquefaction, gasification, and combustion. The second being biological. In addition to the thermochemical biomass to fuel conversion routes, several biological pathways produce liquid and gaseous fuels. Biological routes harness anaerobic digestion and fermentation to produce hydrogen, methane, and alcohol fuels. These biologically derived fuels can be burned directly for heat and power or upgraded to other fuels. An additional microbial route to biofuel production is the use of oil-producing microbes to directly generate biofuel precursors, such as the use of algae via photosynthesis. The 4th step being carbon capture and sequestration. The main carbon capture and sequestration pathways are under consideration for biomass energy carbon removal are 1. Biomass combustion or fermentation with carbon dioxide capture, compression, and transportation to a geological site for long-term sequestration, and 2. Biomass conversion to fuels with biker solid carbon co-production that can be stored long-term as a soil amendment. CO2 capture technologies for biomass, thermal, and electrical power generation are generally the same as those currently under development for conventional fossil fuel power plant carbon capture and sequestration. But these technologies fall within 4 main categories: post-combustion, pre-combustion or gasification, oxy-combustion, and chemical looping. Direct air capture. Direct air capture is largely theoretical technique in which carbon dioxide and potentially other greenhouse gases are removed directly from the atmosphere. The current technique uses large fans that move ambient air through a filter using a chemical absorbent to produce a pure CO2 stream that could be stored. To have any significant effect on global CO2 concentrations, direct air capture would need to be rolled out on a vast scale, raising serious questions about the energy it requires, the level of water usage for particular technologies, and the toxicity impacts from the chemical sorbents used. In addition, safe and long-term CO2 storage cannot be guaranteed, either in geological formations where leakage is a risk, or in products using CO2 where carbon is likely to end up back in the atmosphere one way or another. The fossil fuel industry is attracted to direct air capture because the The captured CO2 can be used for enhanced oil recovery, especially where there is not enough commercial CO2 available locally. Finally, carbon mineralization. Carbon mineralization is an emerging approach to remove carbon dioxide from the air or store it in the form of a carbonate minerals such as calcite or magnesite. In general, the extent of mineral carbonation depends on 1. Available CO2 dissolved in solution, 2. Available alkalinity in solution, and 3. Chemical conditions that foster available alkalinity via mineral dissolution and carbonate precipitation. Although low pH accelerates mineral dissolution and higher pH favors carbonate precipitation, experiments have demonstrated that silicate dissolution and carbonate precipitation can be combined in a single step.
I'll be touching upon the economic side of negative emissions technologies. Costs differ between the various types of technologies. For instance, Climeworks, the company operating the only commercial air capture machine, has reported a cost of $600 per ton of carbon dioxide, while some other organizations have claimed this number to be closer to the $100 to $200 range. Coastal blue carbon projects can cost nearly nothing due to the incredible benefits they offer in return. Since direct air capture offers little in return both environmentally and economically, it will require greater government investment than the other methods. Different methods offer different trade-offs. The more money spent, the more carbon will be emitted from the atmosphere. Coastal blue carbon projects don't sequester as much carbon, but they cost relatively nothing. Furthermore, investments in these projects offer other benefits such as coastal adaptation. Further research in this area could include understanding how sea level rise, coastal management, and other climate impacts will affect future uptake rates. Therefore, although direct air capture methods can prove to be more effective, the extra benefits from coastal blue carbon projects must be taken into consideration. Government funding may be necessary to get research projects on negative emissions technologies up and running. Like many new ideas looking to be put into effect, negative emissions technologies require a great amount of funding. The National Academy of Sciences recommends as much as $1 billion annually in government funding on research on NETs. Considering it is the government's responsibility to ensure the health and safety of its citizens, this could be a small price to pay for the future of the country. Economics continued. Land use change projects would need serious societal adjustments to become effective. Land use change projects such as BECCS, which stands for Bioenergy with Carbon Capture and Sequestration, would require hundreds of millions of hectares of arable land to be successful. Such a repurposing of land would likely disrupt food supply, and it is unlikely that a revolutionary change in diet or agricultural productivity will occur and allow this to be possible. Cost is currently one of the largest impediments in the quest to utilize negative emissions technologies. However, there is still hope. Many countries around the world are in the hunt for effective methods of reducing carbon, and if the intellectual property is held by the United States companies, advances in these technologies will benefit the U.S. economy. Furthermore, this new sector could open up numerous new job opportunities, increasing its positive effect on the economy. Increasing the attractiveness of negative emissions technologies. Economic incentives could push entrepreneurs to find faster and more affordable ways to cut down on pollution. Offering carbon tax rebates or awarding a sort of credit system for carbon reduction would incentivize corporations to join the hunt for effective negative emissions technologies. Also, a reward/punishment system could be installed. A system could be put into place that charges those who emit carbon and rewards farmers and ranchers who agree to store carbon in their soils, as well as investors, inventors, and businesses who help forward the process of developing negative emissions technologies. Without incentives, investors and businesses are unlikely to jump in and help, and they play an important role in the overall process. So what's being done right now? Aviation leads the way. Aviation is responsible for about 2% of global greenhouse gases, and this number was expected to triple by 2050 if no policies were made to restrict them. However, the International Civil Aviation Organization has issued a mandate agreeing to cap emissions from international flights. Their new program, called the Carbon Offsetting and Reduction Scheme for International Aviation, requires all airlines to start reporting emissions and will be enforcing a hard cap starting in 2021. If other organizations start following their lead, then there's a chance that NETs could begin showing a positive impact in the near future. Carbon Engineering Incorporated is getting to work. Canadian firm Carbon Engineering Incorporated has already raised $11 million to commercialize its air-to-fuels technology. Based on estimates, they believe a fully commercialized facility could capture up to 1 million tons of carbon dioxide per year. Stripe has committed to spending $1 million per year on negative emissions technologies. Stripe, an online payments platform, has committed to spending $1 million per year on NETs by purchasing carbon dioxide that has been removed from the atmosphere. They plan to purchase carbon from multiple different types of technologies and have expressed interest in projects that would improve natural carbon sinks like forests and soil. $1 million is a small commitment to pay for many companies and is equivalent to taking 2,000 cars off the road for a whole year.
So basically we have the question of, are nets the only solution to combating global warming and climate change? And in a recent report published by the Intergovernmental Panel on Climate Change, nets were essential to almost every single scenario to keep the warming to 1.5 degrees Celsius or lower. And basically most scenarios also use nets to keep the warming to 2 degrees or lower. And Stephen Pascala, a professor of ecology and evolutionary biology at Princeton University, talked about how humanity continues to procrastinate mitigation, which is basically making it increasingly harder to achieve that 1.5 to 2 degree goal without negative emissions technology. So by the end of the century, to get this goal, we'll need to remove about 40 billion tons of carbon from the atmosphere, which is a really, really high amount. However, in the last 15 years or so, there have been tremendous breakthroughs in technology to solve the issues of climate change. And some of these breakthroughs include solar and wind energy going from being a luxury item that only a few could afford down to one of the cheapest forms of energy ever. And another thing that happened was that we made a lot of discoveries with carbon capture and storage, which has allowed it to become basically a big business today. And so basically making something a big business allows the price to drop and go down as you have many businesses competing with each other, which is the reason for solar and wind energy getting so low, or getting as much lower as they were. And also this year, in the lower 48 states alone, there's about 61 million tons of CO2 going into reservoirs and staying there, which is a really huge number and is a great start. However, we're going to have to continue that if we're going to get to that 40 billion mark by the end of the century. Now, looking at some alternatives to reach the goal, As I said, most scenarios are relying heavily on nets, and more specifically BECCS, which is the bioenergy carbon capture and storage, to reach that Paris climate change goal. However, some scientists are arguing that there should be more mitigation strategies that focus on more cost-efficient methods and models, as this BECCS is rather expensive and takes up a lot of land. So these different cost-efficient models, this whole process is really involved and it's a very expensive endeavor. So being able to be confident in resources available is important to consider when sticking to a plan to reach that goal. And also using integrated assessment models, IAMs, different pathways can be explored that account for chances in population, economic growth, energy demand, and other factors. So IAMs are generally designed to be cost optimal, meaning they basically just prioritize low cost solutions. And IAMs can also be modified to include technical, political, or social barriers to deployment. However, cost remains still the main driver. And being flexible with these societal factors is really important because obviously things are always changing. Society is really dynamic. And being able to account for changes in things like politics is really important. So as I stated earlier, for example, the Trump administration in 2019 withdrew from the Paris Climate Accord, from the Paris Climate Accord, which was monumental as the U.S. is the second largest emitter of greenhouse gases and the only nation to withdraw from the climate agreement. And here's a quote from Dr. Alexander Popp from the Potsdam Institute for Climate Impact Research. And he says, as IAM select technologies on the basis of relative costs, they normally concentrate on reduction measures for which reasonable estimates of future performance and costs can be made. This implies that some possible response strategies receive less attention as their future performance is more speculative, or their introduction will be based on drivers other than cost, such as lifestyle change or more rapid electrification. Now, what Dr. Popp is explaining is that the IAM is basically seeking to lower costs or resources wherever it can for different strategies. And this means that more speculative strategies that may not have a definite cost or definite amount of resources that it'd be using, it can't lower those costs because it doesn't know how much is going to be used, which makes it difficult to cut the amount of resources used. And now Popp is also describing how existing studies hardly look into more aggressive implementation of options, such as rapid implementation of the best available technologies, deep reduction of non-CO2 greenhouse gases, and also how technology development could be more rapid than typically assumed in IAM model runs. So in the place we are now, technology may be advancing much quicker than we thought it would be. And then we accounted it too. So some alternatives, again, to reach the 1.5 degree goal, 1.5 to 2 degree goal. The first would be renewable electrification. And basically all energy sectors would be rapidly electrified, including the heat sector. And these come with technical restraints to integrate different renewable resources that would need to be overcome, as well as by 2030, all new cars would have to be electric. So there are some technical difficulties with this and barriers. However, I do believe they can be worked around with the proper research and investing. Second would be high efficiency. So in this scenario, you'd have the best technologies would be quickly adopted for all energy and material uses, including cement and steel. From 2025 onwards, only high efficient new cars and airplanes would be sold, and only the most efficient home appliances would be used and would be allowed. And third, we have low non-CO2. So this one's pretty basic. We would shift our focus to non-CO2 greenhouse gases and trying to reduce those with the best available technologies and further research on those gases. So basically, instead of trying to take CO2 out of the air and reduce our carbon dioxide emissions, we'd focus on some other kind of greenhouse gas, as opposed to just focusing on carbon dioxide. And as for population, so basically improved access to education accelerates the trend towards reduced fertility so that the global population rises from what it is today, about 7 billion, to about 8.4 billion in 2050, before falling to about 6.9 billion in 2100. And this 6.9 is broadly in line with the UN's lowest ratio for population. And obviously with a lower population comes less greenhouse gases emitted. And lastly, we have lifestyle change. Now this would be just the majority of the world would have to adopt sustainable lifestyles, including by 2050, 100% adoption of healthy diets with lower levels of meat consumption, as well as less private car use and more walking or cycling, with air travel also reduced. So again, this one would be difficult, would take a lot of time. As I said, about 95% of people in the US have access to a private car or a personal car, so they'd virtually have to be giving that up to public transportation. And then looking over at the graph, this is depicting the effects of an increased use of BECCS on land use between the 2 degree and the 1.5 degree goal. And 1.5 degree, as you can see, 1.5 degree scenarios rely much more heavily on BECCs than 2 degree scenarios. And the use of these alternatives also cuts the use of BECCs and the need for agricultural land. And by combining all of these options together, the need for BECCs would be cut tremendously, not quite entirely, but that need would definitely be cut down a lot, which frees up a lot of agricultural land, some of which would be used to replant forests, which again would absorb more CO2, so it's almost like a win-win. But again, like I said, zero BECCS would be just not really possible at this point. We've waited too long. And just in closing, negative emissions technology. So this technology is a very good path to go down for mitigating the effects of climate change. We believe that nets are the best option for the future, and that countries should continue to hold themselves as well as each other accountable, including the US, who, if we're not participating in the Paris Climate Agreement, we should at least be finding other ways to reduce our carbon footprint and make sure that the human species isn't the only one left in the next several hundred or thousand years. We also, we understand that negative emissions technology, it's not a permanent solution. They shouldn't be treated as an end-all be-all. It simply stores carbon. It's not getting rid of the problem necessarily. The only way for climate change to stop is for humans to reduce our carbon emissions and to switch to a greener lifestyle, so that we can dedicate the time and research used for climate change to possibly other world issues. And third, we have more research should be done into this topic in order to find more efficient and possibly more permanent solutions. So as time goes on, technology obviously is going to be advancing, as does our understanding of the world around us. And this should allow us to come across new discoveries that help us find ways to stop climate change for good, rather than having to scramble to make sure things don't go past the point of no return because of our procrastination, basically as we're doing now. And lastly, we have, hopefully humans as a society will not see this as a quick fix to buy ourselves more time. And what we mean by this is, as newer generations are raised, we hope that they continue to take what we've learned in stride and to make more advancements of their own, and to hopefully treat this topic with much more importance and much more urgency than prior generations. A generation that is brought up to respect the earth and everything in it will be one that won't think twice about doing the right thing and making a few sacrifices to ensure that it's around for as long as possible. Thank you.